Hello, who are online, please could you respond?
Yes, ma'am, it's visual.
Okay. So we had last day before yesterday, we had discussed about the this planning of oil planning and hydraulic fracturing. So we'll start with the field development for shale oil and shale gas reservoirs, and to some extent, tight gas reservoir. The field development part is almost similar to the conventional for the tight gas reservoirs, tight oil and tight gas reservoirs. So to start with, this is the brief overview of the presentation. The introduction to oil field development, as we are talking about the oil itself. So stages of the field development, then evaluation of shale for sweet spot identification, which is very much important for development of the field, and then comparison with some shale plays in USA, which are successful. So in this first, we need to know this will be the structure. When you identify the sweet spot, first the depositional environment, then organic geochemical characteristics, reservoir characteristics. So in the progress of the lecture, we'll discuss all these parameters. So first, what do you mean by oil field development? If we talk about this, just a minute. So this is the development is the process of designing and implementing the best ways to extract the oil and gas from a reservoir. It involves a number of steps, including the technical, economical, and environmental factors. And all these factors finally we need to optimize and balance so that finally we can do the development, finalize the development plan. If you look into the activities of the field development, we have a number of stages as I had mentioned. So technical stages are like first we need to identify we go for the exploration that includes the play identification, that's the regional identification and survey. Then we go for the prospect study, where include like seismic interpretation, drilling, and subsurface geology, production test we do. Then we do the evaluation. Once you have the discovery finalized from the exploration stage, we do the evaluation that we call the appraisal stage. Once appraisal stage is completed and it says, okay, your whatever prospect you have identified that is feasible for your production, then we go for the production stage. So this in the development stage and then production. I'm sorry, after evaluation, that should be the development. So once you finalize the development plan, then and implement the this planning for the field development, then you start the production. And finally, when it is economic life is over, we go for the abandonment or decommissioning of the wells. So these in every stage we have numerous studies. We have numerous studies from regional, as I had mentioned, regional studies, geological modeling, bid evaluation, farm in and farm out. So in these stages, when you have the like before discovery, you do the exploration. After these stages, primary exploration, when you do the basin analysis, then we go for the bidding evaluation. So different types of bidding, like prospects are there, licensing policies are there. So in India now we have the NELP, and as well as from 2017 we are using the HELP licensing policy. That is under RSC policy. So these are the this I had mentioned. So for this we need to follow some FDP final field development guidelines, and the purpose is to ensure the hydrocarbons ensure that the hydrocarbon resources are exploitable, and it could be developed, as I had mentioned earlier. And every company, every operators, they should follow the guidelines that laid down by the your national authority or the owner of the field itself. In India, we have the government is the owner of the field. These are the specific stages what we follow in this. So let us what we want to finalize in the field development plan. First thing, whether this field is prospective, that we can produce from there. If we can produce, that's the judgment evaluation we do. If we can produce from there, so what is the amount of hydrocarbon reserve we have? So if it be economical, that we have certain amount of hydrocarbon may be there, but it may not be economically feasible. If it not be economically feasible, we don't go for development of that field. But if it be economical, then we go for the production. So once you are going for the production, what kind of production technology you can implement? How many number of wells you need to drill? What kind of wells you need to drill? Whether you go for fracturing or not, what are the surface facilities you need to have? So all these are planned in the development stage itself. So here also we do the economical analysis to see the cash flow throughout the life of the reservoir, life of a particular field, not reservoir, I should say the particular field, and accordingly we plan for the cash flow also. So in this development plan, these are the key factors we need to consider. First, the location of the field, size of the field, because economics are dependent on these factors itself. What is the lithology? Lithology is important. Location is important because you see, if we have, say, in land, some reservoir in land, some field is in shallow water or deep water, then your this economics will be different, and development plan will be different. Size of the field is important because how much you are producing, that depends on your sales profile and others, that will depend. Lithology is important because not only for the drilling, during the well completion and during the production, the dynamics of your formation depends on the lithology. Pay zone means what is the pay zone thickness you have, what is the pay zone volume, whether they're connected or they are layered or they are in series, whether you are compartmental. So the strategy, well completion strategy and development plan, like how you are producing, that depends on your pay zone. Fluid properties is important, because you are making the money on the by selling the fluids itself, what's the oil and gas. So fluid properties, we need to know like how, what rate you will produce, how much you will produce, what is the quality, these are important. Drive mechanism, because whether later on what should be the self flow life, later on what the your technology or your pressure maintenance technology will implement, that depends on the drive mechanism. It tells about the reservoir energy, natural energy. Traps, so the traps also, like what kind of trap you have, if it be say structural or your lensed kind of trap, so the strategy will be different depending on traps. Logistic, where you also all these the transportation and other logistics, storage, all logistics, these are important parameter. Socio-economic condition and political situation, these are nowadays, that how the oil price is being changed, and the policies of each and every government will differ depending on this condition and political situations itself. So coming now, we are let us back to the shale, as we are considering we want to develop the shale oil reservoirs. So again, I am showing this slide. I have shown you my first presentation also. So why I'm showing here, because the difficulty level in shale reservoir development is much higher compared to the conventional. That's because of its heterogeneity, uncertainty. If you look into this, risk is high in the shale reservoir, and you will understand when you will go through the development and analysis of the shale, then you can understand what are the difficulties involved in this. So these characteristics, as mentioned, this high uncertainty and less economic than conventional because the volume of hydrocarbon per acre feet is very much less compared with the conventional here. You need to do the hydraulic fracturing and that impact your environment. So these uncertainties, risk and economics involved into this make this development is more difficult compared to the conventional one. This one I'm skipping. Already have studied, no, the origin, where from we are. So source rock, we are talking about the source rock, not the reservoir rock now, because our field, when you talk about the shale oil or gas, that oil or gas is trapped inside the shale itself. So that's the source rock. And this, like when you talk about this, we need to know the petroleum origin because when you go for the exploration, for a conventional reservoir, that's not so important when you evaluate the reservoir quality. This is not so important, but for shale, this is important because you are producing from there indigenous oil and gas, whatever present in the pores, small tiny pores in the shell, present there, we are producing there. So if you have heavy oil, it will be really difficult to produce. And if you have gas, you will be happy to produce compared to your oil itself. So this evaluation of source rock is important. So we'll first discuss about the source rock evaluation. Already Professor Sheng has mentioned you by showing the example of bread. So how much it is cooked? It is undercooked, immature, matured, or overmatured. Okay, so here, if you look into this, this will like discuss this from this slide itself. If you look into this, when you are going deeper and deeper, your maturity level is increased, and this depending on the temperature, you can have what kind of oil or gas you can have. So when you find a shell somewhere, then we need to check where in which zone it is, whether it is in oil zone, oil window, gas window, immature window, or mature window. If it be immature, we'll never go for any further evaluation through them for this. And this migration, when after this generation, we need to know whether migration occurs or not. Why? Because migration we talk about for the conventional reservoir, how much it is migrated to your reservoir and it is trapped, how much it is trapped. Why this is important for shell? Why this should be important for shell? Because we want to produce the retained amount of hydrocarbon generated in the shell itself during its maturation stage. That's why if you know how much is migrated, you can determine how much is retained within the reservoir. And that will tell you what is the hydrocarbon in place in the shell itself. So whether this is economical or not, that will calculate later on. So that's why migration you need to study. So these are the like in shell we have the oil and free oil or gas in the tiny pores, and if we have the gas, some of the gas remains in the adsorbed condition mostly. So because of small amount of pore volume is less, storage capacity is less in shell. So if you have the gas, if you have the in gas window, so you have to determine the adsorbed state, how much gas remains adsorbed in the shell, that also you need to determine. So these are the screening parameter you need to go for when you want to develop a shale oil or gas reservoir. So in the surface, subsurface, economic, these parameters we need to study. So first thing is we'll discuss about this subsurface parameters. Then this one economic parameter, then we go for the this different laws, environmental laws, and other land occupation and other act will study. So first thing here, I want to discuss these subsurface parameters for this development planning, because it will be otherwise it's very lengthy. So first thing is when you are going for development, we need to identify the sweet spot. So what do you mean by sweet spot? Sweet spot is this one, because shale, we can have a large area that can be spread over, the shale can be spread over that. But everywhere we cannot have the retained amount of hydrocarbon may not be good enough. Even the shell may not be matured enough in different stages. If we look into, like, if we think of our Campe basin itself, if you go from northern part to southern part, so northern part, if you Balol and other, if you look into this, there we used to have heavy oil. So the maturity level is less. If you come for the Ankaleshwar and the southern part, the oil is good, oil is of good quality. That means the maturity level is high. So in a particular basin itself, the shale we can find there, the maturity level is different and the retained hydrocarbon may be different. That's why we need to identify out of this large basin which spot is ideal for the development. So these are the evaluation, as I had mentioned, for the large area remaining oil and gas in place. From there, if you look into this, this will be the cumulative production to that. This could be proved reserve we can have out of this large LF. So this is proved reserve is so much, only small amount is there. That's why you need to identify where into this will be your sweet spot itself. So we'll start from the basin evaluation itself, because in the exploration we need to understand what basin itself, then we'll sequentially we'll go for this. So first thing, the basin model we need to make for identification of shale what we have and their preliminary qualitative identification of the shale where we can have the matured shale we can find. So if you look into this figure, the left side figure, you can see this is one like a maturity profile along the Cambe basin. This evaluation is done by us. So from here, if you look into this, when you are going deeper and deeper, your maturity level, this is the yellow one is the over matured stage. And this dry gas, this is orange one, dry gas, the red one is the wet gas, and late oil, this early oil, this blue one is the immature one. So shale formation in Cambe, you have different layers we have from about 1700 to more than 3000, more than 3000 and below maybe. So there we can have large thick shale is there, but all are not matured enough. So here, how can you identify that? Because these are identified from different kinetic parameters, how they undergo the maturity level as we are talking about this. So from this, we evaluate from the temperature, pressure conditions, the geothermal condition, we do modeling from there. So here, this is the basinal identification, as I had mentioned, this regional identification, regional studies we do for identification. So once we do identify that we have the shell which could produce this oil or gas matured, which undergoes the oil window, matured windows that can produce oil or gas, then we go for exploration well. So once you have drilled an exploration well, you have collected the shell sample, then we want to identify quantitatively. That's the qualitative analysis we have made here, basinal analysis, the large area we have identified. Then we drill the exploratory wells and we collect the sample to identify really they are matured or immature one. If they are matured, which window they have undergone. So this one we do this rock eval analysis. So total organic matter, and then we do the rock eval analysis. We identify S1, S2, and S3. S1 is the free oil or gas remaining within the shell itself. So this gives you how much oil you can produce. If you have identified some cell and you determine the S1 per like how much amount of oil or gas is there per gram of your shell, then we can say this is the free oil or gas retained in the shell. And if you start production, then you can this much amount of certain percentage of this you can recover. Another thing, this is the H2 that gives you, if you do the pyrolysis, then how much of that could be produced. Okay, so this and Tmax we determine at during the pyrolysis itself. This kerosene they undergo pyrolysis and they can produce the this hydrocarbon as well as the further like pyrolysis can produce the carbon dioxide at in presence of oxygen. S1 and S2 we determine in absence of oxygen. Okay, so Tmax is the another parameter which tells you the maturity level of the shell itself. So this, when you have studied this, we identify the window whether this is good or not. So if the TOC, total organic matter, so content, if you are determining if it is more than this, so it's fair quality S2 we have determined, and we have determined this category. So we are categorizing which category it falls into shell. So it's very good. If it be very good, TOC should be greater than 3 generally. So in this window, you can have TOC generally 0.5 and above. That can give you some amount of fair. So it's you see this is in fair quantity. And S1 will tell you whether indigenous or it is transported from somewhere. From this calculation, S1 and TOC cross this axis. If you plot it, then you can see indigenous or non-indigenous. Non-indigenous means it's transported from somewhere else. So this is hydrogen index is another parameter which will tell you whether this is oil prone, gas prone, or which kerosene is what type of kerosene. So we can identify this window from here. And this Tmax and hydrogen index plot will tell you this identify whether what is the maturity level. If the temperature is below 430 in S2, then it's in the immaturity level. So if your maturity level will be high when you are going, this is the oil window, this is the gas window, and over matured window will be this one. So this is the like Tmax and production index. Production index is the like if you have free gas, S1 indicates the free oil and gas present, hydrocarbon we better say, present in the shell, and S1, S2 this is the production quality or productivity index of productivity of the shell itself. So this production index will determine the free oil and gas divided by total amount that could be present after pyrolysis. So it can undergo cooking again over the time. So this is the amount we determine. So productivity index, these we identify, we determine those, and then we evaluate our shell whether it could be produced later on or not. So this is another parameter, masteral groups, vitrinite reflectance. So if you look into this, these are the vitrinite reflectance. This will tell you what kind of masteral groups we have. And so masteral groups, once we are identifying, so kerosene type of kerosene we can identify here. If it be algal, then generally oil producing. If it be some others plankton type, then it will be gas origin could be there. So this from this identification, you can see the vitrinite reflectance. You can identify visually also, and from there we determine the vitrinite index from reflectance. So once you determine TOC, S1, S2, Tmax, hydrogen index, productivity index, generation potential, and then we determine the oil saturation index. If it is oil prone, so now we evaluate whether it is economic or not. So this oil saturation index that tells you 100 milligram of hydrocarbon per gram of TOC. If it be greater than 100, then it will be we can economically produce. But other factors we need to consider in terms of oil present there, we can say, so it's good for the production, move further for the development. Okay. Got it, this one? Oil saturation index, why you are determining this one? So if it be below that, we won't produce from there. We'll not move further. So then we determine, like, once we have this one, how much per acre feet, how much oil or gas could be there. So hydrocarbon initially in place. You see here, when you are determining S1 or S2, that is retaining there, how much return there. But some of the gas already expelled, oil or gas is already expelled. So hydrocarbon generation, we determine from this is like zeta, that's the this is the expelled amount. So hydrocarbon generation, so we determine from this one hydrocarbon generated S2 TR by 1 minus TR, this is the calculation, and then we determine how much return amount is there. That's equal to the S1 itself. So once you know the S1, when you are calculating, you are taking out the core, that time itself some amount may be lost. So when you do the calculation of hydrocarbon in place, generally we take 35% may be lost or during the retrieval of core or cleaning, etc. So this one hydrocarbon retained, we calculate as this one S1 into 1.35. That's the assumption 35% is lost there. So corrected hydrocarbon expelled, then we calculate from this one. So expelled amount that could be migrated to some conventional reservoir. So this one, we make this table to identify this one. So then we do calculate the this one example is there, how we can determine hydrocarbon resources in place. So here you see hydrocarbon oil in place. So this corrected hydrocarbon written there multiplied by, we have multiplied per gram of TOC, so it's per gram of rock that is calculated here. So then we can calculate how much hydrocarbon is there, hydrocarbon in place is there. So one example, when we have calculated the density of oil, this one, rock density is the one, and S1 we have calculated. So from there we have this HR1, this is 2.24 we have calculated. So from there, oil in place is calculated as this 3.53 million barrels per 640 acre feet area. So per acre feet, 0.005 million barrels. So you can say 5,500 barrels per acre feet. So we need to now find out whether it's economical analysis we need to do, whether we can produce and multiplied by recovery factor, that will give you how much, whether it is economical or not. So this calculation we need to do for this. Now, once you see that, okay, hydrocarbon in place is good enough, we have the economical amount, then we go for the mineralogical and morphological characteristic. What is the porosity is there, whether we can do fracture or not, because unless otherwise you do the fracturing, we cannot produce from there. So how do you analyze? So porosity, if we look into this, porosity generally, as we had mentioned, the porosity is very less. So can you use the conventional porosimeter or permeometer to determine the porosity? Its porosity is very small, permeability is the nanode level. So conventional porosity permeometer generally cannot work. So we can utilize different special porosimeter or permeometer calculation, permeability calculation to know that. So for this, generally, initially we visualize by visual interpretation. We identify what are the mineral matters are present there and what are the pores present there. You can see these are the pores. We can calculate these pores by visual interpretation, image analysis we can determine. this kind of pores you can have. These are the pores we have. These are the pores we have. You can identify that. And the mineral matters, we identify here different crystals are there. These are good for us as this can give you the brittleness index. We'll calculate the brittleness index. Next, we determine the mineralogy present there. What is the mineral matter? What percentage they are present? And this clay matter also we calculate from here. So this, for calculation, we determine the quartz, carbonate, and clay. We identify. So from there, brittleness index is determined. Here, some examples are given, like from some Cambay shells. If you they compared with different USA shell. So where we are. So this is, if you look into this Utica, Second White Speck, Eagleford, Wyo, Hassan Valley, so New Albany, these are the different shell reservoirs in USA. So this tells you where it's falling, whether we can go for the fracturing or not. So brittleness calculation, brittleness index we do calculate from the core analysis as well as the log analysis itself we can carry out. Brittleness average we calculate. These are the calculation we do. Different types of calculations are there. These are the all parameters are taken, so this could be the better way to do determine the calculation. And this is the brittleness average we do calculate from the log itself, log approach. So if you look into this, so from brittleness index, if you calculate, this will be your values. So it should be generally 45, minimum 45 brittleness index to have a good fracturing. If it be below that, that means your clay is more and your calcite or your quartz, these are carbonate quartz, these are less, so fracturing would be difficult for you. So it's not feasible for this. Effective fracturing is not feasible. So these are done. Once it is done, then we can go for this production. So here you see some samples we analyzed. So somewhere OSI, as for this this region, if you look into, we had identified 1975, oil saturation index is higher, but brittleness index is less than 45, but close to 45. It's 40. Here, brittleness index is good, but OSI is less. So this is, we'll go for this one, but not for this one, because oil, if oil not be there, so it's not useful to do the fracturing. So this is better to do the fracturing here. So your sweet spot may be this one itself. So once we have this fracturing capability is there, then we go for the determine the porosity, pore structure, and adsorption characteristics if you have the gas. Because the porosity, permeability, we need to determine. That's very much important for your production. The matrix, as this is dual porosity system, so matrix porosity is also important in addition to your fracturing porosity. And here, if we have seen in the this itself, some this you can see this one. You may have some fracture also. These are generally developed in the this organic matter. Also, you can see some fractures. So for this, these are, if you look into this, this is the organic matter. You have some development of the porosity. This is microfracture in the clay. So different types of pores are there in the shell. So this should be identified in the FECM first, as I had mentioned before. But in addition to that, all could not be quantified in the matrix itself. So we go for low pressure nitrogen adsorption, and for determination of the specific pore volume, and then specific pore porosity, determination of specific porosity. We identify the pore distribution, like pore diameter distribution, and from there we determine the permeability using this equation. So R35, that's the percentile, the 35%, we determine this is from the MICP. This is mercury intrusion porosimeter, because simple low pressure nitrogen porosity that could tell you the porosity level is higher, generally micro. Micro level you can determine, macro level you can determine from the mercury porosimeter. So different types of porosimeters are used to identify all ranges from micro, meso, and macro porosity range. So from there, we determine the permeability. So if you look into this, the permeability matrix permeability is so less. This is determined from using this equation. This equation, there may be some other equation modification may be there. So this is the porosity, this is the permeability porosity we determine from this porosimeter. So these are the process we identify, and permeability is determined from there. In addition to that, if you have the gas, adsorption is another important parameter for the shale gas. So we need to identify whether how much gas could be adsorbed there, and the surface morphology is very important for that. So this AFM, another technique is used to determine the hewness, like morphology, how heterogeneous it is. So this is determined from here, and from here also using image analysis, you can convert them to the porosity. So the FESM and AFM both are used to analyze the image analysis and determination of porosity. In addition to that, your low pressure nitrogen adsorption or mercury porosimeter, because these are the destructive method, and this is FESM or AFM. If you use, these are non-destructive method. Like you can use intact, some core sample you can use. These are some example of pore size distribution and pore volume with variation in, these are the micropores, mesopores, and macropores distribution. So we identify from there. These are the compositional control over porosity, pore characteristics. So if your like vitrinite reflectance, clay content, pores, these differ, then your porosity will discuss. These are the special type of analysis we do. Okay, so here when you are talking about this this development plan, so first the exploration stage, we have identified where we can have the oil and gas, and so this kerosene maturity is screened for the shale for its hydrocarbon generation and production capacity. Mineralogy that provides the information about the frackability of the field. Then pore size distribution indicates gas storage if you have gas and oil storage, and transport capacity. Adsorption capacity, that will be for the shale gas itself, not for the oil. For oil, that could be important for if you go for enhanced oil recovery, the adsorption characteristic to be studied, because unless otherwise you have seen this oil is very much less in the tiny pores there, unless otherwise we implement it is difficult to produce. So in that case, if we use different types of chemicals, adsorption of the shale in the shale and clay must be determined here. So permeability determination to be determined for the fluid transport capacity, types of pore responsible for various mechanisms of diffusivity of gas and oil, and if you use, you are studying already that carbon dioxide injection you have studied, no? So diffusivity of gas is important in that case. Pore volume that of oil and gas storage per acre provides the economical viability. After this, further development, we go for this followed by this characterization, street port identification. We need to identify what should be the number of wells, well spacing, and type of well. How do you determine when you go for the well type of well? How do you determine whether you have this vertical well or horizontal well we want to determine? How do you determine that? Do you have any idea? When you are given, say, different types of well, okay, say in some particular formation, you have to judge whether we should go for vertical well or horizontal well. First, what the thing first will do? How do you identify that? How do you evaluate? We have given, so they are of different shape. So quantitatively, you have to mention, no? Thickness is one parameter. You have to identify what is the productivity index ratio, preferential productivity index, no? So if you have some vertical well and horizontal well, so from the productivity index itself, we compare which one will give you better result. So if it be better, then we will go for the this horizontal or this value productivity index of horizontal well to vertical well. If it be higher than greater than 1, then we'll go for the horizontal well. This is technical one. When you talk about the thickness, the economics is also important, no? Horizontal well cost is very high. So those things to be considered. Then fracture design. How do you design the fracture? We are talking about the multi-stress fracturing, no? So that's costly. How do you control that? Then development of surface facilities. What are the facilities you need to have here? What are the facilities, extra facilities compared to the conventional? What could it be? Compared to the conventional one. Surface facilities, is there anything special here? If it be volumetric reservoir, for conventional reservoir, do you need for water separation, too much separation is needed, or water treatment? If it be shale oil, do you need that? Yes or no? What for? Why? This is because during the fracturing, we cannot recover during the flow back. We don't recover much of the water there itself. So during production, we produce that water in addition to oil. So separation and treatment is very much important. So the development of surface facilities, these are also very important for here. So you see here, because the recovery, primary recovery is poor here, so we need to go for the EOR at the beginning stage itself. So it should be considered in the field development stage. So what kind of, how do you screen that EOR? What is the screening criteria for EOR? Can you use polymer here? Polymer flooding, do you use here? Why not? Polymer flooding, why not? What are the screening criteria for EOR? For chemical EOR or any other EOR, what the criteria? What do you do? First thing, oil characteristics, because the mobility ratio you have. Then what are those? What else? Polymer clog the pores. We have the tiny pores, no? We have very tiny pores. So they are polymer you cannot utilize. Then, so first thing is the, like, when you are going for the EOR, first thing is the oil. So mobility ratio is one of the very important parameters. Then what are their temperature? Temperature, because if you go for the chemical flooding, temperature is very much important. No, temperature is. So another thing, depth is another parameter. No, why depth? So because if you go for say carbon dioxide EOR, okay, so you need to have minimum pressure for minimum miscible MMP, minimum miscible pressure. No, so these are the different parameters. If you have the fracture, can you use EOR? Generally fracture is over. Will you go for the EOR? Conventional one, high fracture, normal fractures are there. There you may lose because the injected fluids may move through the fractures only. No, not through the like matrix wherever you have the pool of oil is present there. So that may be bypassed. So those things to be taken care of. No, here also, what we are considering here? I'm not visible there, probably. Okay, so these things to be considered here. Generally, why we use foam flooding is very important for here, no? Carbon dioxide foam. Why this is for? And what we need to consider for foam flooding. So this, when you are doing this, because generally for the conventional, we think of the EOR during the development plan. But here you have to do, because from the beginning itself, we go for the enhanced recovery. Similar to your, say, Acharya Bagmer. So there you have the, from the beginning itself, we implement the EOR. No, why that is for? Because that's the heavy waxy crude. Mostly waxy crude, because of that, it cannot flow. So we need to have some pushing or implementation of thermal EOR this balloon. We are utilizing thermal EOR, no, because that cannot flow. So these for when you are developing the field for the shale oil itself, we need to think of what kind of, you need to screen the EOR technology the beginning itself. Okay. So these as now I need to discuss actually some questions are there. So these are the when you talk about the development stages, all these should be carried out first and then implement it in the field itself. Economic analysis. Okay. So I have made some questions I need to ask. So please answer if you can. What are the main stages of field development? Starting from, we start development plan from exploration. We need to have the data. No, exploration, appraisal, development. This is the life cycle, life cycle of this one. Field development stage, what we do? Exploration, we collect the data, then evaluation, and then planning, and economic analysis, techno-economical analysis. These are the stages. Significance of S1, S2 in identification of sweet spot. What they tell us about. S1, what it tells about? Pre-oil or gas present, hydrocarbon present in that. So that generally, if you identify, discover some shale, oil or gas reservoir, that only we can produce. And S2, what it tells about? Is the potential. S1, S2, total is the generation potential. So if that is there during the maturity level for long, then H2 also may be converted to S1. So that gives you the generation potential itself. What is the role of mineral matter in cell field development? Role of, yes, please write whoever not here. Mineral matter knowledge is important for fracturing. Yes, we determine the brittleness index, so that if brittleness index is not good enough, so it cannot do the fracturing. So that is, and without fracturing, we cannot produce. Can you use conventional porosimeter or permeameter to determine the porosity permeability of shell? No, because they are, before fracturing, they are very small amount is there. Like porosity, pore diameter is also very small. No, so conventional porosimeter, permeameter, we cannot be used to determine that. So special porosimeter, permeameter we can utilize. Some other permeameter, like you can light scattering or other techniques you can utilize. These are the conventional one. So how do you calculate the hydrocarbon influx and the reservoir? So we determine from the S1 and the lost amount we calculate, and then we can determine from there. Oil saturation index, what is that? And why this is important? That indicates what is the volume of economical volume of hydrocarbon present there. What is the value? Minimum value, what should be? Generally, in general, 100 for economical one. Why the primary recovery of shale oil reservoirs are very poor? Because of low permeability porosity, and in addition to that, the retained volume in shale is very less, no? Because porosity is very less. Porosity tells itself the storage capacity, so amount is less. Brittle index, can you define? If you are given the quartz, calcite, clay, minerals, from there you can determine the brittle index. Okay. minimum value brittleness index 45 in general. It may differ to some extent depending on the economics and others. So all these values we are the thumb rule we use. No, every individual reservoir, these are different. So economics, in addition to that, we calculate the economics. So techno-economical feasibility we do. What is the need of basin modeling for shale oil gas reservoir? That's the regional level identification, no? Regional level identification. Because over the region, we need to identify if we have a basin and if we have some shale formation, then we need to identify where it's that and what is the capacity, what is the maturity level of that. If it being matured region, then immature window, we don't go for that. Okay. So, and whether oil or gas is there or not, so we determine from there. So, any other query you have? Any other question? Anyone else who are online? Otherwise, I'll stop here. Okay, thank you very much.